We will look at some examples now. So we have an indoor environment where the rate of inflow of a compound from a window is 0.1 microgram per second. Further, X is produced due to indoor air reactions at the rate 1.5 microgram per second. So this is like a production term. It is observed that outgoing air carries X at the rate 0.8 microgram per second. So outgoing air. X is destroyed by chemical reactions at 0.9 microgram per second. The question is, what is the rate of deposition if indoor source of chemical is 0.2 microgram per second, and assuming we have a steady state. So the first step to solve this kind of problem would be to make again our conceptualized figure. We are going to make our indoor environment, or the environment we are looking at, and now we will identify the sources and sinks. So rate of inflow of a compound, so we are talking about F in. This is equal to 0.1 microgram per second. Next thing we can search for is a production term. So further, X is produced due to indoor air reactions at the rate 1.5 microgram per second. So this is our production term. .5 micrograms per second. Now the other source would be emissions. So let's see. It is observed that outgoing air carries X. So this is outgoing. X is destroyed by chemical reaction. So looks to be a loss. What is the rate of deposition? This is another loss. If the indoor source of chemical is 0.2 microgram per second. So here we are talking about an indoor source. So this is more like an emission term. This is a source, not the summation source. This is the indoor source. So this is the emissions that are occurring indoors. So often it is important to read the question in the context of the question and then relate it to our conceptual framework, because everyone may not be using the same term as we do. So indoor source of the chemical is 0.2 microgram per second. So I'm going to add . Now let us find the sink terms. It is observed that outgoing air carries X at the rate 0.8 microgram per second. So we are looking at outgoing air. So this is our F out. F out. So F out is 0.8 microgram per second. Now we can have a reaction loss term. So X is destroyed by chemical reactions at 0.9 microgram per second. So this is our term that we have seen as L in the previous slides. So L is equal to 0.9 microgram per second. Then there is another deposition. What is the rate of deposition if indoor source is 0.2 microgram per second? What is the rate of deposition? So our deposition is actually unknown, and this is something that we have to find. So now what we can do is we can set up our mass balance equation. So if mass inside of chemical inside this room is m, we have dm by dt is equal to F in plus P plus E minus F out minus L minus D. Now what else is written? This is our mass balance equation, and we know we have to assume steady state. So dm by dt is equal to 0. So now we have the building blocks of our solution. So I'm going to make some space here. So I'm going to use the values now of F in P and E. So we have 0.1, which is F in. P is 1.5 plus E, which is 0.2 minus F out, which is 0.8 minus L, reaction loss, losses by chemical reaction is 0.9 minus D equal to 0. So I'm going to bring D to the other side of the equation. So we will have D is equal to the sum of these three. So 1.8 minus these two, which is 1.7. So this will be equal to 0.1 microgram per second. So D is 0.1 microgram per second. Basically, we have to identify the terms, which term is which number, then set up the mass balance equation, and then solve for the unknown, which is D. So in this case, I have written also typed it out, which is dm by dt equal to E plus P plus F in minus chemical loss minus deposition minus F out, which is equal to 0 here. So we have this 0.2 plus 1.5 plus 0.1, which is 0.8 minus 0.9 minus 0.8, so minus 1.7. Unknown is D, which is 0.1 microgram per second. Now we have another example. So the rate of inflow of a compound from a window. So again we are talking about indoor room, and air is coming, and together with the air X is coming, and this rate is 0.02 milligrams per hour. Okay. Then X is produced due to indoor air reactions at 0.015 milligrams per hour. So production term. It is observed that outgoing air carries X at the rate 0.047 milligrams per hour. So this is our outflow. X is completely gaseous and has a negligible deposition velocity to the floor. Okay, so looks like there's no deposition, and is destroyed by chemical reactions at a rate 0.008 milligram per hour. Okay. So that's our reaction loss. It is found that the concentration of X is in the room and it's increasing at a rate 0.001 milligrams per meter cube per hour. Given that the room is 50 meter cube in volume, find the rate of emission of X. So again, we have done all our equations in terms of mass. Now we have been given a little bit of trick in which we have been given the rate of increase of concentration in the room, which is 0.001 milligram per meter cube per hour. So not to worry, first we will make, again, because concentrations are not balanced, mass is balanced. So again we will make our mass balance. So we have mass which is inside the room, we have F in, and again F in is given as 0.02 milligrams per hour. Further, X is produced at rate 0.015 milligrams per hour. So X is produced. P is equal to 0.015. I'll make a erase. 0.015 milligrams per hour. Okay, what about the emissions? Find the rate of emissions. So we have emissions is unknown. Okay, let's see losses. So it is observed that the outgoing air carries X at 0.047 milligrams per hour. So we have our F out. F out is 0.047 milligrams per hour. Any reaction loss due to reactions? Let us see. X is completely gaseous, negligible deposition velocity and is destroyed by chemical reactions at 0.008 milligram per hour. So our L here is 0.008 milligrams per hour. Okay. Now any deposition, it is, so we have here X is completely gaseous and has a negligible deposition velocity. So here we are going to have negligible D. So let us consider D as going to 0. Okay, sorry. So we have all the items here. Now let us set up the mass balance equations and see what are the knowns and the unknowns. So we are going to set up the mass balance equation. dm by dt is equal to E plus P plus F in minus L minus D minus F out. So what are the things that are unknown? F out is known, deposition is known, loss is known, F in is known, P is known, E is not known. Or I'll just use a question mark here. E is not known. What about dm by dt? So we have been given some information here. Concentration of X in the room is increasing at 0.001 milligram per meter cube per hour. So what exactly is M? We have seen M is equal to C times V, where V is 50 meter cube. So now dm by dt is d of Cv time by dt, which is equal to C dV by dt plus V dC by dt. So dV by dt, now volume is not going to change. So dV by dt is basically 0 because volume of the room is constant. So we have dm by dt is equal to V dC by dt. dm by dt is V dC by dt. So we will rewrite this. So all this will be equal to V dC by dt. Now what is dC by dt? 0.001 milligrams per meter cube per hour. So what is V dC by dt? Let us just fill the numerical value. So it is V, which is 50, and I'm going to write the units so that it's easier for us to follow, meter cube multiplied by dC by dt. So it is 0. Cross sign 001 mg per meter cube per hour. So this way. So 50 multiplied by 0.001. This value is going to be 0.05, and the units will be meter cube and meter cube are going to cancel out. So the units will be milligrams per hour. So these are the same units as all our loss processes. See, milligrams per hour here, milligrams per hour here. So the units are all fine. So we have the value of V dC by dt now. So we can go ahead and find our unknown. I am going to enter all the values. So E actually is unknown. So E plus P. P is 0.015. 0.015 plus F in, which is 0.02, minus loss is 0.008. Loss is 0.008. Minus deposition, which is negligible. So no deposition velocity, meaning there is no velocity going down, so that is 0 deposition. 0 minus F out, which is 0.047, and this is equal to V dC by dt, which was 0.05. So basically we get E is equal to, or we will go E, we will go one more step slowly. E plus 0.035 minus 0. This would be 0.08, 0.008, 0.047. So this would be 15 carry over 1, 5, 0. So E plus 0.035 minus 0.055 equal to 0.05. So now we will have E equal to 0.05 plus 0.055 minus 0.35. This will be equal to 0.07 milligrams per hour. So this is our answer. So just for illustrating one more time, we will do dm by dt equal to sinks minus sources E plus P plus F in minus L minus D minus F out, and M we will write as C times V. This remains the same, E plus V plus F in minus L minus D minus F out. C dV, so D of CEV by dt will be C dV by dt plus V dC by dt, where this will get cancelled out because the volume is constant. And then we will plug in all the values, and basically we will end up with the same number, 50 dC by dt E plus P plus F in minus L minus T minus F out, and get the answer. So there were some twists in the questions, in that instead of mass there was a term concentration written, and also instead of using a steady state it was time variable, but the value of dC by dt was given. So the key here was to convert dC by dt to dm by dt. We were given dC by dt, we actually want dm by dt, because the balance is always by mass. Mass cannot be created or destroyed. So we had to convert this dC by dt to dm by dt, and we can always invoke mass is equal to concentration times volume. So then once we did this kind of step, the answer then came out by itself, because it was then just a matter of doing plus and minus, and we will arrive at the answer. So in summary, in this lecture, we have learned to set up simple mass balance models in terms of one box only, and we have had done the concept of steady state and time variable mass or time variable concentration. Now in the next phase we will do the residence times, rate constants, and half-lives.